today we will discuss about tree data structure. So in the previous class we have seen what is tree and what are the types of trees. So where do we apply tree data structure? Gentlemen, so where do we apply tree data structure? So what is a tree data structure? It represents a hierarchical representation. So tree of the unit is mainly a hierarchical representation. So where do we use this kind of representation? Family tree is general example in terms of computer science. So have you heard of file system? What is file system? File system, for example, if you take, if you want to locate a file, say for example, let me say I have saved a file called as ds.doc inside desktop. So what is the location of this file? How do we trace the location of this file? So for example, in the desktop I have saved this document. So if you right click on this document, you can check location, right? So if you check that location, how it will be displayed? Displayed like this, right? See, colon, desktop, file name dot doc. So this is your file system. So file system of being it locates it locates where that particular file is stored. So this is the location of this particular file. So this file system is stored in the form of tree data structure. So here this C is your root directory. So C will be your root directory. So from C we have desktop. So this is the edge of the branch. So desktop. So, and in your leaf node we will have ds.doc. So this is a tree data structure. So this is one application of file system. So it is also used in networks. So if you take, if you want to establish a path from SNS college to surroundability, so this is one terminal and the surroundability will be another terminal. So between these two terminals we will have several other terminals. So each terminal will act as a node. And the connection between two terminals are the edges. So these are the various applications of trees in computer science. So if you take, in terms of problem solving, here we apply tree data structure. For constructing expression tree, we can use tree data structure. Yes. So we can construct an expression tree for infix expression as well as for postfix. We can apply tree for constructing expression tree for any kind of expression. So let us take one postfix expression, for example, AB plus CD star minus. So this is a postfix, right? So how do we call this as postfix? So operator is followed by the, operator is followed by the operands. So operand comes first, followed by the operator. So similar to the conversion process where stack is applied, if it is an operand, you will push it into the stack. If it is an operator, you will drop the first two operands from the stack. So this is your stack data structure. So let me tell only for this you solve for the MIT. So what is first input? It is your operand. So you push it into the stack. What is the next input? It is operand. Push it into the stack. Next you have to pop these two from the stack. So since plus is an operator, we will pop these two from the stack. Actually, you will apply like this. So if this will be your left side, left subtree. This becomes your right subtree. This becomes your root. So plus is your root. A, B. So the topmost operand will be your right node. So the one below the topmost will be your left node. So this is an expression tree for this. So can you continue for this expression AB plus CD star minus.
First operand push into the stack. Operator pop the top two functions.
It is wrong, right? So after putting this expression tree, again this has to be pushed into the stack. So since these two are popped, now the stack will look empty, right? The stack will be empty. So now this is your topmost. This is an input. This entire subtree is considered as an input. So the next operand you are reading will be pushed above this. So next star is an operator. So pop D and C. So in next what you have to do?
extend minus.
Minus. So this becomes your left sub 3. This becomes your right sub 3. So the final answer will be like, how does it look like? So let me write here. So minus, this entire part is your left sub 3. And this entire part is your right sub 3. So this is your expression 3. So you remember pre-traversal? Pre-traversal. In order, so can you write in order traversal for this? Left sub 3, root, right sub 3. See, for each sub 3, when you are writing the traversal, put a parenthesis. Start with the parenthesis and give it parenthesis. Root node. So A, minus. So for given expression tree, when you perform in-order traversal, you will get infix expression. So for each subtree, if you put parenthesis, that will constitute an in-order expression. So when you write in-order traversal, you will get infix. If you write post-order traversal, what is a post-order traversal? Left, right, root. Again, left, right, root of the entire tree. So this is the corresponding post-order in postfix expression for this expression. It is obtained when we write post-order traversal for this. Write pre-order traversal for this, minus, plus, AB, again root, left, right. So when pre-order traversal is done, we will get prefix expression. Clear?